In this section, we're going to review batteries and give you a little bit of background so that you know what's inside a battery and hopefully relate that back to what you already understand with respect to galvanic or voltaic cells. The real interesting aspect of batteries isn't necessarily what's going on inside, because again, that's just related back to what you already know about galvanic cells, but the interesting thing, in a lot of respects, is just the packaging. You can imagine making a galvanic cell like we've made before with two beakers and a U-tube and electrodes. You know, that's neat because it provides electricity, but hauling that around and using it for your cell phone or something would be a little bit annoying and wouldn't work so well. The neat thing about batteries is how the galvanic cell is packaged so that it is portable and compact and gives you the voltage you need in the way that it does. So here is just an old-fashioned battery. The technology behind this battery has been in place for a very long time, and in reality very little has changed. You can see a picture of the battery here and the half reactions which are taking place inside the battery here. Simply zinc being oxidized at the anode and ammonium being reduced at the cathode. You get zinc becoming zinc 2+, ammonium becoming ammonia, and you also have hydrogen. Again, the packaging is what's impressive, and you'll see that you have a zinc canister which serves as the canister and as the anode, and the other components, the ammonium, is in a paste inside the battery, and that's in contact with a graphite rod that just serves as an electrode to take electrons from the zinc to the ammonium. And of course, when you connect this into the battery through a circuit to this end of the battery, you get the current to flow and you get the voltage that's shown here. Now, an interesting thing about this, you know what ammonia smells like. It stinks. You know that hydrogen is explosive. This battery produces something that smells very bad and a gas that explodes. Another interesting component of this battery is those things need to be contained so that there's a hydrogen trap. It actually reacts with the manganese 4 oxide, and there's also ammonia trap. You know from our complex ion experience that zinc 2+ complexes with ammonia, so the ammonia also gets trapped. So again, the neat part about this is just how it's contained. You don't have to memorize battery reactions or be able to completely diagram every aspect of a battery. It's not why I'm showing you this, but I do want you to have an overall feel for what's taking place in batteries and to understand that they simply are galvanic cells packaged in a neat way. You know when you go to the store to buy batteries that there's a significant difference between the price of alkaline batteries and other batteries. The other batteries are these type of batteries. Some people will call them flashlight batteries. The alkaline batteries have relatively similar components, but they're slightly different. Alkaline batteries, again, zinc's involved at the anode, and here is the cathode reaction. Notice that the voltage is essentially the same, so that turns out to be same. So you can use old-fashioned batteries or alkaline batteries for essentially the same applications. Another thing that's interesting, so it doesn't matter if you get a AAA or a AA or a C or a D battery, they all have the same voltage. The thing that's interesting or that's significant, you might wonder why an alkaline battery would cost more, but the thing that's significant is that the voltage performance is more stable for an alkaline battery. So I could just draw a diagram here, say this is voltage and this is the amount of time that you draw a certain current from that battery. Okay, in an alkaline battery the profile looks something like this. That wouldn't be exactly right, and this is meant to be constant along here, but when the voltage drops off for an alkaline battery, it drops off relatively quickly. The old-fashioned battery profile, the one on the previous page, so I'll try to start about the same voltage and go, but then it just sort of phases out with time. And notice they've gone dead about the same time interval, but also notice if I have a certain application that requires this much volts for that to work, this battery is going to work longer than, try to do kind of a similar there, you're going to cross that threshold quicker with the old-fashioned battery. So an alkaline battery gives you longer, more stable performance than an old-fashioned battery. The problem with this is you don't get much warning before it's shot. And so sometimes people refer to the old-fashioned batteries as flashlight batteries. Just use them for flashlights, and flashlight will get dim but continue to work for a relatively long time, and you get some warning that your flashlight batteries are going dead long before they actually really do completely go dead. So anyway, that's the difference in the profile. This is why alkaline battery would cost more. Now, based on your expertise with what you've learned in this chapter, why would this equation, this overall cell reaction, give you a more stable voltage for a longer period of time than this reaction? Okay, so you've got a cell reaction there. You've got this cell reaction, and this one's more stable. Have an idea of where you would look to answer this question? Well, I'll give you an idea. Nerst's equation answers this for us. Notice that we're going to get a certain voltage from this cell reaction, and it's based on the E naught for the cell, just shown here. Actually, I could put a naught there, and Q, relative reactants and products. But notice what you have happening with the states here: solid, solid, liquid, solid, solid. In this case, Q is going to be equal to 1. You plug in 1 for all solids and liquids, which means this term for this reaction is going to be 0, and E will stay constant at E naught. The significant development of alkaline batteries is that you have solids and liquid in every case for your reactants and products, so their activity remains the same at 1 until you essentially have run out of reactants, the point where this reaction has to be totally dead. Whereas in this case, you have an ion there, something in solution there. That's a gas that's going to be trapped. So Q will not be equal to 1. As you build up products and consume reactants, then E is going to continue to decrease until you reach an equilibrium situation. You have no more voltage that's generated from that battery. Okay, so anyway, a little background there. Mercury battery, again, it's just another example. So you have zinc involved also. These are the batteries that are usually pretty small. Watch batteries, calculator batteries, things like that are usually mercury batteries. But again, just gives you the voltage. You can see what the cell reaction is for those. The packaging is the cool part. Now, rechargeable batteries are interesting in that they work as galvanic cells as they discharge, but they're also set up so they can be electrolytic cells as they recharge. So in reality, you have a discharge direction and a recharge direction for these batteries. In discharge mode, you have a spontaneous reaction, which will happen until you run out of reactants and build up products. At that point, then you can recharge the battery by changing the polarity and driving electrons in the non-spontaneous direction and remake your reactants. So again, the overall cell reaction, it's neat. Now you can see what's happening inside the battery in your car or your four-wheeler or those type of things that use lead storage batteries. So that's great. And you can also see what the voltage is for it. But the real genius of these is the engineering and how they're packaged so that you can, in fact, drive their products to reactants once that you end up with the depleted reactant. So you can continue to use the same package over and over again just by letting electrons flow in a certain direction when you need the electricity, driving those electrons back in the opposite direction. If you ever tore into a lead storage battery, you would see, and let's say it's a regular 12-volt car battery, you actually would see 6 individual cells. They're packaged in different ways in different brands and types of batteries, but the reason for that is if you need a 12-volt battery and your half reaction can deliver 2 volts, That would mean that you'd need 6 individual cells inside that battery. If you take 6 cells that have 2 volts each and hook those up in series, then you end up with a total of 12 volts, and that's what you'd see. And you have overall reaction here. You lose lead, and you lose lead 4 oxide as you discharge. They both go to lead 2 sulfate. You recharge the battery, the lead 2 sulfate. Some of it is reduced to lead, some of it's oxidized. Interesting setup for lead 2 storage batteries. Okay, there are other types of rechargeable batteries. Nickel cadmium batteries are the old-fashioned kind. These have voltages of about 1.4, so if you go back, remember our old-fashioned batteries? We had the nickel cadmium batteries. That cell gives you about the same voltage that we had for those, and so these used to be used for same applications that old-fashioned batteries did. Problem was it's kind of low for those applications, and sometimes you're barely over the threshold of them being usable. So they didn't have to discharge very much to the point where you had to recharge them again. Didn't work really great. Some applications they were okay. And nowadays we have lithium batteries, lithium-ion batteries, and this is a significant advancement in battery technology. Now that you know a little bit about galvanic cells and you've seen other types of batteries, it actually would be interesting to go look up on the internet diagrams of lithium batteries and just see the way that they're configured and arranged. Again, it's neat engineering, science advancement, but you always look forward to my art, I know that. And in a lithium battery at the anode, you do have lithium. Another thing about lithium is it's a very light metal. You have, let's see if I can draw this so that it's sort of even. Between the anode and the cathode, and this is just like a polymer that will conduct electrolyte or conduct ions, you have this electrolyte polymer referred to, and over here, at least in one form, you have lithium sulfide at the cathode. So when this battery discharges, it goes through there, okay, it's going through your cell phone. Perfect. Then electrons would flow from the anode to the cathode. That means that this electrode, lithium, would be oxidized, and what you would have is lithium ions which would move or flow through this polymer electrolyte. So the battery actually works when you discharge with lithium ions flowing in this direction through this polymer grid, and when you recharge it, electrons are pushed back and the lithium flows back and redeposits on what was the anode and now would be the cathode in the charging direction. So again, the new technology is great. You end up with contained system that keeps everything intact in a way that it can be discharged and recharged many times, which fits our modern lifestyle and use of electronics. So not a great diagram, but hopefully it's good enough that you go look up a real diagram and try to relate that back to these half reactions and the way the cell is actually set up. So again, I don't expect you to memorize a lot about batteries. I do expect you to understand the concept of batteries in general, the concept of rechargeable batteries, where in one direction, as you discharge, you have a regular galvanic cell, and as you recharge, you have an electrolytic cell where you drive things in the non-spontaneous direction. And you can correlate that to all the other things you've learned in galvanic cells with what happens at the anode, what happens at the cathode, what's being oxidized when it discharges, what's been oxidized when it recharges. So batteries give you a good opportunity to ask a few conceptual questions if you're a teacher dealing with the basic principles of redox reactions. So get a good general understanding of what's going on with batteries and how it relates to what you actually already know about redox reactions.